Hello everyone, I'm Isaias Huerta and I'm going to present my work entitled Intersubject Clustering of Brain Fibers from Whole Brain Tractography. The main goal of this work is the creation of an efficient clustering for multi-subject whole brain tractography. The main output are representative clusters that include fibers from most of the subjects. The main difficulties in addressing this problem are the high amount of data to be processed, which increases with the number of subjects to be analyzed and the quality of the dataset, as well as the high variability between subjects. The technique can be divided into three stages. In the first stage, we reduce the amount of fibers using an intra-subject clustering. In the second stage, we reduce the dimensionality of the data by conversion to a latent space. And in the third stage, we gather the subjects and perform a density clustering on the reduced data. We use tractography datasets with about a million fibers per subject from 79 subjects of a hardy database, representing in memory more than 70 gigabytes of information. To compress the tractography information of all subjects while maintaining the underlying structural information, we apply a fast clustering method called ffclust on each of the 79 subject datasets, obtaining about 10,000 clusters per subject. As the clusters are compact along their trajectories, each cluster is represented by its centroid. The use of the ffclust technique requires that each fiber be sampled to 21 equidistant points. This fast fiber clustering achieves good quality through a technique based on the fiber point distribution. It can be divided into four steps. First, k-mean is applied to some fiber points. Then preliminary fibers are generated. Small clusters are reallocated to larger clusters. And finally, candidate fiber clusters are merged. So, as a summary, for each subject we obtain about 10,000 clusters. For each one, we calculate centroid. And using this data, we continue to the next stage. Even with this reduction in the number of fibers, computing the distance matrix is a time-consuming task. In order to reduce the computational cost of centroid pair with distance computation, a reduction of complexity is applied to the centroids by means of an LSTM autoencoder. The purpose of using the autoencoder is, after training, to compress each of the fibers to a reduced dimension space called latent space. As each original fiber is represented by 21 points in 3 dimensions, each fiber requires 63 float numbers. The selected autoencoder architecture uses a latent space of size 7 floats, which is 9 times smaller than the original size. This dimensionality reduction enables the clustering of a larger amount of fibers by reducing space computational requirements. When compressing the data in the latent space, we force them to be represented according to their distinctive features, simplifying the clustering task. To get an idea of how our data is arranged in the latent space, we use DSNI visualization of a subset of the obtained fibers, showing a better agglomeration of the fibers in the latent space compared to the original fiber space. Hence, before applying a density clustering, the fibers and traces from all the subjects were encoded to the latent space. Density clustering seems to be suitable for intersubject clustering because possibly common to most subjects become more dense in the same space. A density-based clustering algorithm that is noise-aware and robust is HDV-scan. If we perform this algorithm without adding subject information, it is likely to obtain clusters whose fibers come from few subjects. To reduce this probability, we introduced a modification to the HDV-scan algorithm aiming to move away the points that belong to the same subject. The original HDV-scan algorithm first modifies the space by making scattered points further apart. To do this, it uses a distance metric between points called mutual reachability distance, where core is the distance from A to its k nearest point, and D is the original distance metric between A and B. In order to disperse the points whose neighbors are from the same subject, we redefine the mutual reachability distance. Let equal the number of k neighbors from the same subject and A, and lambda a factor that range between 1 and 2. Lambda will be 1 if all its key neighbors are from different subjects, and it will be 2 if all its key neighbors are from the same subject. We multiply this factor to the corresponding core. The HDV scan parameters are the mean cluster size and the mean samples. The mean cluster size defines the minimum number of elements in clusters, and the mean samples determine how conservative the clustering is going to be. The higher the value, more points are considered noise. To prevent a high score in a small cluster collection, we add a penalty. The higher score is obtained with mean samples 1 and mean cluster size 70. 917 intersubject clusters were obtained in 1.3 hours for stage 1 and 152 seconds for stage 2 and 3. Here we chose some examples of the obtained cluster with a representativeness of at least 70 out of the 79 subjects. And this figure shows in the right an intersubject cluster corresponding to the inferior frontal occipital fasciculus, and in the left we show the cluster separated for each subject. And here we show another example of resultant intersubject cluster corresponding to the arcuate fasciculus. To validate the approach and compare it with other methods, we generated a synthetic population of 20 subjects with the labeled fascicles. So to simulate variability in the fibers, we changed another autoencoder similar to the presented in phase 2, but this time with a latent space of 21 and using for training a deep white matter bundle atlas. After training the autoencoder, for each fiber of the atlas, we add Gaussian noise in its latent space and reconstruct it. The reconstructed fiber looks similar to the original one, but with a slight deviation in its shape and position. In addition, the amount of fibers is also variable for each subject and follows a Gaussian distribution. We compared the results with 5 different intersubject clustering techniques using the 20 simulated subjects. All of them first performed phase 1 and then used the intrasubject cluster centroids as input for the further steps. The selected methods aim to perform a comparison between the use of the modified HDV scan and K-means, and the use or lack of dimensionality reduction with LSTM autoencoder. In addition, we added a method that applies the FF-class algorithm a second time on the centroids of the intercluster obtained for all subjects. Results shows a better performance for the proposed method. In conclusion, we present a new intersubject clustering for tractography dataset using 3 phases. We apply our intersubject clustering approach on a merged fiber tractography dataset of 79 subjects from a Hardy database. Our preliminary results show that our scheme is able to identify known deep white matter bundles with high level representation in the subject collection. Also, when comparing the proposed method on simulated data with other clustering strategies, our method provides the best precision and F1 score. Future work will be focused on more detailed evaluation and improvement of the algorithm.